This is Mrs. Palmer-Quay with the second video for Module 5. In this video I want to talk a little bit about atomic structure before I get into talking about atomic mass. Remember that Dalton in 1808 proposed the atomic theory that the atom is the smallest particle of an element that still has the same physical and chemical properties of that element. He couldn't see atoms. We still really can't see atoms, but computers can provide us an image by the use of a scanning tunneling microscope, which uses changes in electric current that is being impressed across the atoms in a structure to give us an image of what that structure looks like. So we have some scanning tunneling images here, one of gold from the very beginning days of this process, and then a more recent one of the silicon crystal. Inside the atom there are three subatomic particles. There have been a number of different researchers that have devised experiments to bring out this information. We will cover some of that in class, but as you go on in science you might learn even more of the details. The three subatomic particles are the proton, the neutron, and the electron. The proton is considered a large particle, large in quotation marks, because we're talking about, of course, something so small we can't see it. And it has a mass of 1 atomic mass units, 1 AMU, which is the same as 1.67 times 10 to the negative 24th grams. So it is a very, very small mass. But in comparison with the other particles, it has a large size and a large mass. Protons carry a positive electrical charge, which is given a value of 1 when we're talking about charges in an atom. The neutron is a large particle about the same size as the proton, and so it would have a mass also of 1 AMU, and it carries no electric charge. It is neutral. The electron is very small. Its mass is approximately 1/2000th of an atomic mass unit, and carries a negative electric charge of 1. What is interesting about your protons and your electrons is that the proton, even though it's much larger, has a positive electric charge that is exactly opposite in size, in magnitude, as the negative electric charge on the electron. So they balance each other out, even though the masses are very different. In fact, here's just an illustration I found about the relative mass, that if protons and neutrons had the mass of a baseball, then electrons would have the mass of a grain of rice. So you can see there's a very large mass difference between these subatomic particles, protons and neutrons on one side and electrons on the other. The subatomic particles are arranged in what we call the nuclear model of the atom. Ernest Rutherford was the head researcher on experiments that determined this. And the model says that there is a tiny, dense central core in the atom where you find the protons and the neutrons. And then the electrons occupy the space around the nucleus. And space is very true, that there is a lot of empty space, a void or a vacuum in an atom. If an atom was the size of a football stadium shown here, and the electrons were occupying this space out in the stands of the football stadium, the nucleus would be the size of the marble down there in the center of the football field. And so it is much smaller than the total atom, but the nucleus is where you have the larger subatomic particles compared to the tiny, tiny, tiny electrons that are way out there far away. So the atomic number, going back to our periodic table, the atomic number represents the number of protons in an atom. And the protons are what determine the identity of the atom, that all atoms with the same number of protons are the same element. If an atom has 6 protons, it is carbon. It is nothing else but carbon if there are 6 protons there. Typically the number of protons equal the number of electrons when you have a neutral atom. When there is no charge, it is not an ion, but it is neutral, the protons and the electrons then are of equal number, so that the electrical charges balance out. So looking at your typical square here from a periodic table, you have your atomic number, the smaller number, the atomic symbol, of which I hope you have memorized it and can look at that and say, oh, Ag, that's silver. And then the larger number you will see is the atomic mass. So the atomic mass is calculated by counting up the total number of protons and neutrons. The electrons are so small they just are not counted at all. Because the number of neutrons can vary, not all atoms of an element are identical. And so the atomic mass values are actually averages, and that's why you see decimal points in the atomic mass values given on the periodic table. They are not, since the atoms are not all the same in any one element, you cannot have a whole number when you're taking an average. Here are the three common isotopes of carbon. Isotope is the word we use to describe atoms of an element that are not identical. But what is identical, of course, is the number of protons. In each of these isotopes, you see there are only 6 protons, because if it was a different number, it wouldn't be carbon. What is different is the number of neutrons. 6 neutrons in this isotope, 7 neutrons here, and 8 neutrons in this third isotope. And so in order to distinguish between isotopes, if it's necessary to do so, we use the atomic mass from adding together the protons and the neutrons as part of the name. So we have carbon-12, or carbon-13, or carbon-14. Carbon-14 is radioactive, which is why it can be used to do radiocarbon dating, and you may be aware of carbon-14 in that context. The amount of these isotopes varies quite distinctly in carbon. Almost 99% of all carbon is carbon-12, which, depending upon the precision found in your periodic table, that's why the atomic mass for carbon may be given as just 12.0, or it might be 12.0 and another number if we are going out to more decimal places. Carbon-14 has a very low abundance, 1 part per trillion, but again, since we're talking tiny, tiny atoms, that still is quite a few carbon in anything because there are just so many atoms in you to begin with. This table shows in graphic form the different isotopes that many of our elements have. If the ones like carbon, you can see it's basically all blue, that is the stable carbon-12 element, and then there's a tiny little slice of some of the other isotopes. But you see over here mercury, this one, there's several different isotopes in relatively large quantities available. If this chart was larger, you could see that some of the numbers telling you the atomic mass of the different isotopes, some of them are in black, which indicate a stable, not radioactive isotope, and the ones that are in red, like every single one over here on uranium, indicate radioactive isotopes. And then finally, let's talk about molecular mass. If you add up all the masses of the individual atoms in a molecule, you will have a mass value for that molecule. And this is something that you will be doing for the rest of the course. We will be doing a lot of calculations where you need to know the molecular mass. You go back to the periodic table and look up the individual atomic masses for each of the atoms that are in a molecule. For example, for water, H2O, you have 2 atoms of hydrogen, each with an atomic mass of 1.01, and 1 atom of oxygen with a mass of 16, so that your atomic mass units, your mass of 1 molecule of water is 18.0 AMU. Remember, when you're adding significant figures, you have to use the least number of decimal points in your answer, so we only have 1 on the 16, so you only can have 1 decimal point on your answer. Sodium chloride, something we've mentioned many times. Sodium's atomic mass is 23.0. Chlorine's atomic mass is 35.5. So the molecular mass of 1 molecule of sodium chloride is 58.5 atomic mass units. When you have a substance like this lead nitrate that we worked with in lab, where you've got some subscripts, you need to include those subscripts. When it's outside of parentheses, treat it like a factoring situation where you're going to have to multiply it in by both atoms, thinking back how you do that in algebra, so that it would be lead at 207.2 plus 2 nitrogens, 14 AMUs each, plus 6 oxygen, because there's a 3 and a 2, you'd have to multiply those together, and that comes to an atomic or a molecular mass of 331.2 AMUs. So if you know the chemical formula for any molecule, you can calculate the molecular mass with a little help from your periodic table. So this covers what I want to say for this video, introducing you to atomic mass.